All right, welcome everybody. You pumped? Yeah? All right, so let's start. Welcome to the Reactive Streams talk. It's me. I'm Victor. Work for Typesafe. And
I'm Roland, leading the Akka project at Typesafe. And so we are going to talk about Reactive Streams today.
And specifically why you should care. So enough talking. Right? So how many of you are ready to see some code? Awesome, let's go.
Yeah, so we thought we'd start out by just throwing you in the deep end of the pool. It's completely natural if you don't understand all the details just yet. There will be a second part of the talk where we go through some of the details.
Someone will pick you out of the pool.
Yeah. So let's just try to write a simple streaming program. So what we will need to do, so this is of course being based on Akka. Reactive Streams is a standard which is general and so on for many different languages. But we can only demonstrate it with an implementation, and the implementation which we're going to use is Akka Streams. And everything in Akka is basically based on actors, as you might know. And in order to create actors, we need an actor system. So first, let's create an actor system. So we create an actor system with some funny name. And then when we write down some stream statements, we describe how a stream is supposed to work, what it's supposed to do. And that will have to be transformed into actors in some fashion. And that is described by a so-called flow materializer. So we'll need that up front. So we create a materializer, and the materializer is very configurable. You can have different ones. We just need to tell this one what it's going to use. We're just using all the defaults, nothing fancy. So what I've created up front is a little domain model that we will use throughout this presentation, which is that of a bank transfer. For no real reason, it was the first thing which came to mind. We have a transfer, and the transfer has a from account to account currency and some amount. The screen here is really small. So that's just a long. We all know, don't put currency values in doubles, right? So this is a long. Now, we also want to be a bit type safe, so I made case classes wrapping strings for the account and the currency, which just have a string override so that they look nicer. And then we have some select currencies, completely random selection from where the Akka team is. And then we have generators here for a transfer. A transfer will just generate some account, some other account, and a currency, and just a random number up to 1,000. And that will be our transfer. We don't do any fancy analysis on that. We just want to print some of them. So we make a flow. A flow is the abstraction in Akka Streams, which describes what kind of stream transformation you want to do, and also what you want to start from. And we want to start from transfers. So we give it a function that tells it how to create a transfer. So this is all nice.
So what do we have now, Roland?
What do we have now? We have an error.
Awesome.
Yeah, that's cool. That's live. So of course I need to import the bank here. Now I have a flow. So this flow doesn't really do anything, really. It's just a description of how to create a stream if we asked it to. We haven't asked it to do anything yet. Now, what you want to do with it, we may just print it. So we call for each print line. If you're used to Scala collections. So when you call a collection for each print line, it will just print all the things. If we run this, then actually nothing will happen. I don't even need to show it to you because really, literally, nothing will happen.
5 minutes for nothing, right?
Yeah. Okay, I'll speed up a bit. So the point is for each produces something when it's done, and that needs to be consumed to start the stream running. So now we have actually a program that we can execute. Doing that, well, we see it's running. It's running as fast as it can, and it's producing these transfers.
So an infinite stream of random transfers in 6 minutes.
Yeah. So I need to kill this one. And we can do many things. We can, for example, take just 10 of these, right? The expectation would be that if we run this, it will produce just 10, and then it will not produce anything any longer. That's cool. But the application is still running. Why is it still running? We have here, I mean, there's something here which we can try. Print line done, right? What happens? Oh, it's done first. How did that happen? Well, it's a stream. It's executing in actors. It's done asynchronously. It's the flow setup which we write down just describes what we want to happen later, right? So the application is still running because the actor system is still running. And to do the final thing here, we don't just consume. We say when we are done consuming, so on complete, we call something. We are not interested in whatever the result was that came out of this stream, because for each just gives it a unit at the end when it's done. What we want to do here is system.shutdown. Now, if we run this program, well, yeah, you see it only on this thing here. It's not actually running anymore. Still, the done happened first. Then executed the stream, and then the application shut down. So, how are we? Yeah, we have three more minutes, right?
Sure.
So, I've collected a few things for the second step, some of the things you've already seen. Now we want to do something more interesting, a little bit more interesting. We have this flow, which you have seen, which creates transfers. We don't consume it just here. We say to producer. To producer gives you a data type. So this materializes the stream. It creates this actor, which will call the transfer function. And it will do so when it is asked by a consumer that we attach. So we need to do something to make it actually run. But we don't want it to run at full speed. We want it to run like one per second. So what we do is we make a stream. There's another way to start a flow. You can give it a time interval, and then you need to say you need to give it a function to generate the element, which shall appear 1 per second now. So this describes a flow that will have 1 tick per second. Now, what we can do, we have this input stream, which is as fast as it can go, and we have the ticks. How do we tie them together so that the transfers are not produced faster than we get the ticks in? Well, in collections, when you want to, you have one list here and one list there, and you want to pair them up, there's the zip combinator. So we take the ticks and we zip it with the input, and then, well, you know the drill. We zip it, then we print the result, and then we need to consume it to make all of it run. And now it prints 1 per second. This is actually a little bit remarkable, because we have produced here, we have written down, I need to actually stop it. We need to look at this one. We created a producer of transfers which was arbitrarily fast, and now we just reined it in and said, okay, I just want 1 per second. There's not more allowed to come out, but where do all the other values go? The machine doesn't run out of memory. The trick is that these streams obey back pressure. The zip operator will actually say, don't give me more than 1 per second, because on the other side I get only 1 per second. And this is why it works, and it works nicely.
And also why you should care about reactive streams, right?
Yes, coming back to the title of the talk. Yeah, we can do another fun thing, just very quickly. I'm stealing minutes from him now. So we want to do something a little bit more. Move the code up. I'm trying. Yeah, thanks. So we want to ask a web service which gives us currency conversion rates, and then we want to transform them. So first of all, we don't want to flood this service just yet. So we say tix zip input, and then we map it. We want to apply a transformation on this stream, but the web service, of course, is a nice reactive one which gives us a future. It's not a blocking call. So there is a map future. And I actually would like to write this down like this. So zip gives you a pair of the left and the right, as usual. We're not interested in the tick. And we are interested in the transfer. Let's call it T here. Then I have prepared a little mock web service, which has a method, convert to euro. We take the currency out of this one, and we take the amount out of this one. And this gives us back a future. Now, it would be quite boring because this is a future of long. It just gives us the converted currency. So we map this future. What happened here?
Nice.
Yeah. I know you're using a different IDE, so. I quite like Eclipse, so really. I've done all my coding in Eclipse for the past 2.5 years at least or so. So what did I want to do? Yeah, I want to make a transfer. So this is an amount which we get back. It's the converted one. And from that we just to show what it came from, we make a pair of the incoming transfer, and then we make a new one. Transfer T from, T to. Then the currency now is euros, and the amount is the one which we got here. And then we just for each print line consume, and that should give us one transfer per second. On the left you see the incoming ones with all the different currencies. On the right one you see them exchange rate converted to euros. So this would conclude the first part, like getting your feet wet with streams, some of the things you can do with streams. Now, we've been talking about streams a lot. So let's back up a bit and take a look, what do we mean by stream? I find this quote to be really, really instructive. You cannot step twice into the same stream. The stream is something which is, by its nature, the metaphor that we mean is this flowing water, and when it's flowed past you, it's gone. You will not get the same water molecules the next time you step into the stream. I don't know whether he knew about molecules, but that's what he meant. So, what is a stream? It's an ephemeral flow of data. Once the flow is gone, it's gone. It's possibly unbounded in size, just like the streams we take the metaphor from. Examples might be stock tickers, like the stock exchange always produces data, or sensor inputs could be, you don't know when it ends. You can have finite streams as well, but that's just a special case. Also, you have seen all the things I did with the streams in the coding was not focusing on the entirety of data which will be in the stream. That would be what you do for collections. You focus more on transforming them. You describe only what you want to happen in different stages along the way as the data flow through, like the riverbed, so to speak. And of course, streams can be formed into processing networks. You can have arbitrary, you have seen some of these combinators so far, and there will be more later. Contrast that with what is a collection?
Is that an open question? Anybody?
What is a collection? I tried to find out. It was kind of hard. I was Googling that. I was expecting a wealth of academic papers describing precisely what a collection is. I was not successful. So the Oxford Dictionary was the first thing I turned to. Then a collection is a group of things or people.
Like an audience.
Yeah, exactly. We know exactly who's in the room. right? I mean, you have these badges. So we know everything about you. It's a concrete group of people or things. Wikipedia. A collection in computer science is a grouping of some variable number of data items, which is very much in the same spirit. Then the only other relevant hit I found on the internet, you might be surprised why I cite this. This was the first which came up, right? From Backbone.js. Collections are simply an ordered set of models, which is again the very same spirit. And then, well, we turn to kind of the Bible, because collection appears somewhere, right? That was before the Scala collection, so it must be older and better. A collection has certain methods as defined in Java util collection. It has a definite size of type int. It's really finite, right? It provides an iterator which can visit all the elements, and it has a contains method. You can query who is a member of the collection. So that is a collection.
What if it throws unsupported operation exception?
Then it is still a broken collection. So when you deal with collections, you have certain expectations which have been formed in your brain since you were, well, I mean, I started programming at the age of 6, right? It doesn't matter when you started, but at that point, or shortly thereafter, you started like having these expectations, what a collection looks like a sequence of things. And an iterator, you go over it, you expect it to visit all the elements. If you like take a list and you take the head and the tail and you put them back together, well, you expect the result to be the list which you started out with, or at least equal to it. The contents of a collection does not depend on who is visiting it or when the processing happens. It does not depend on how fast or how time-consuming the calculations are that you're doing on this collection. Now, there are some unexpected things when you think about how streams work. So streams are ephemeral. They are flowing past. If you subscribe to a stream at a certain point, you will not see the elements which flowed past before you subscribed. So in a sense, if you like take the concept of iterating over elements and you say a stream, you can just iterate, well, that's not what you're used to. When the subscriber is not fast enough for processing, things will have to happen. The stream will have to back up, or you will have to lose elements. I mean, if you have this stock ticker and prices are coming in and you cannot process them fast enough, you will lose updates. You will just not see all values. When the stream doesn't flow fast enough, we will see examples of that later. You have a sensor and you want 1 value per second, but it doesn't produce a value every second. You could make a stream which does that, which just repeats the same value twice if needed. So if the stream is not fast enough, you could see more elements than were in there originally. Now, looking at Java 8, there was this package Java Stream which was introduced. And it's also interesting to see that the stream interface is not derived from collection, which tells us stream is not a collection. Interpreting that in this is a relationship that inheritance means. And they even say that streams differ from collections in several ways. They don't focus on storage. They're functional in nature, so you describe the transformation. Laziness seeking, you describe the transformation before it happens, so just saying .map will not actually run the transformation. They can be possibly unbounded in size, which is not true for Java collections. Well, in this concrete case, a Java 8 stream is consumable. You can only do one terminal operation on it, and then it will be consumed. It will throw exceptions if you try to reuse it. So this means that streams and collections are not really the same thing, but you can build bridges. So a collection can be used as a source for a stream. You can go through a collection and stream all the elements. Or if you hook a processor into a stream, that processor can put everything it sees into a collection. So you can go both ways between streams and collections. But saying that streams are just lazy collections is wrong. That is not the right thing to do. It evokes the wrong associations. So please keep in mind, streams are not collections. Otherwise, you will get burned.
Thank you, Roland. Let's just take a couple of seconds and let it sink in. All right, so we've been doing quite a bit of this reactive thing. I don't know if you've come into contact with this before, but what if streams are really useful? Like, just consider that. What if streams are really, really useful, and how would we use streams with reactive applications, like the fundamental traits of reactive? How would streams have to work in order to really well fit into the reactive ecosystem or be a nice player in the reactive ecosystem? And I think fundamentally, the core problem with trying to use streaming with reactive applications is getting data across an asynchronous boundary. And an asynchronous boundary means that there is something else on the other side that is potentially operating at a different speed, right? Something over there, and it might be slower, it might be faster, it might not even be there after a while, or the guy on the other side might disappear as well. So how do we build streams that work across asynchronous boundaries? So we want to push something over to the other side. What if that thing is not ready? If we do blocking calls, that would be in deadlock country, right? Doesn't work. Don't do blocking unless you have to.
Yeah, that would invite the wrath of the clan.
So if we just try to push, the producer is just pushing, 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 and the receiver is too slow, then we'll have to buffer, right? We have to have some leeway in between the producer and the consumer. And of course, at some point, like how much memory do you have on your computer? Is it close to infinite? Anybody?
I want your computer if you say yes.
So at some point, you'll have to decide what you do once you run out of buffer space. So generally, that means that you need to do either both buffering and dropping, or just dropping, because you can't do just buffering because you will just run out of storage. So that doesn't work either. What do we do now?
Magic.
Magic! Reactive. So if we want to non-blockingly produce stuff over some asynchronous boundary, and we don't want to have things dropped, and we don't want to have, well, we do want to have infinite memory in our laptops, but until they actually invent it, we don't want to run out of space. So we want to be able to say, you can use n space, and we still don't want you to drop anything. This sort of leads us into the Reactive Streams initiative. How many of you have heard about Reactive Streams before today? Cool, awesome. That's
Very cool.
Anyone that didn't? Hey. Cool, it's a good day for you. So the Reactive Streams initiative, this is the quote from reactivestreams.org, is an initiative to provide a standard for asynchronous stream processing with non-blocking back pressure on the JVM.
Quite a mouthful.
Yes. So, who is doing this stuff? So we collected a couple of interesting people, some really good engineers that are doing some very similar stuff. You might recognize some of them. And this is not like your pointy-haired boss spec group that sits around drinking coffee, eating cake all day. It's engineers working to solve real problems together. So, what is it? How does it work? Well, essentially, we all face the same problem. We have this asynchronous boundary. We have these things that we try to connect together, and we need to do that in this non-blocking, non-lossy, non-infinite memory way. And we're all building tools for our communities, right? So that's a good thing, have that in common. So a common solution would essentially benefit everybody, right? So if we can agree on how we would do this, then we can interoperate, right? There's also a good blog post by John Brisbane on like the way that we collaborate on this. And also, if we have the same solution and we're all building the same things and they have shared interfaces, then if somebody is, for instance, using Project Reactor, has something that it wants to connect to some Akka thing, that it wants to connect to some RX thing, that it wants to connect to some Vertex thing, that should just work, right? But wouldn't it also be sort of super awesome if you were to have it in the JDK, right? So everybody can do this. So what we're going to try to do is to try to package it so we can hopefully propose it for a future JDK version. So how do we do this? Like, we have a group of people have the same problem. We have tried to minimize the problem formulation. We have the same kind of motivation, and we should just sort of go, right? So how many of you have seen a spec that was large? Okay, it's a sizable amount of people. How many of you have tried to implement a large specification before? Okay. How many would volunteer to do it again? Two guys. Awesome. So if we try to minimize the interfaces and just making sure that we have the bare minimum, the old, it's perfect when you can't remove anything else. And if we try to sort of specify that in a really good way so that it's easy to implement it, it's not sort of, well, sort of, yes, and maybe, perhaps, and sometimes, then it's easier to implement the spec and knowing that it actually works. But also, I find it sort of amusing that there's tons of specifications out there created by engineers, and there's no automated testing to verify that the specification is being followed by an implementation. Isn't that weird? Like, it should just be there, right? So what we're doing is we're trying to come up with a good TCK so that if you implement this and you want to verify that you've understood the specification right, there's a high chance that the TCK will actually tell you that, no, you should really do this instead. So if we're minimizing the interfaces, and we have this specification that is very nicely done, and we have a TCK that verifies everything, and what about the API, right? What if Groovy people want to use Reactive Streams, and they have their own ways of defining APIs and DSLs for how to do it in a Groovy idiomatic way, or Scala people have a completely different way of expressing the same thing in an idiomatic way for the language. We don't want to specify for everybody how their APIs should look, because that would just mean that nobody would find it interesting. It would be like the lowest common denominator API. So we've actively resisted adding anything that has to do with end user API. This is for implementer only. So reactive streams are asynchronous. Doesn't mean that they are concurrent. They're asynchronous and non-blocking. So we have some sort of flow of data in this stream. But what if we also have some flow of demand, right? What if there was something on the other side of data? If we try to minimize coordination and contention, it means that it's easier to optimize because there are fewer moving parts and people that could do things with things while you were doing something else.
We're also trying to be nice to the CPU, to be honest.
Yeah, be nice to your CPU. It's doing a lot of good stuff for you.
Yeah.
And if we define it in a sort of a message passing friendly way, it doesn't really matter where the producer lives, if it's on the same, in the side of the same actor or inside the same thread or the same CPU, the same node, same application, same data centers, same continent, same planet, same universe, right? Doesn't really matter. As long as you have a good connection, right? So let's think for a while. If we have data that we're trying to send in one direction, that's the direction of the stream. What if there was another stream that we're going in the opposite direction, that we're expressing the demand? Like, does this thing actually want any data? So our data elements flowing downstream, our demand is flowing upstream, and data elements flow only when there is demand. And data in flight is bounded by the signal demand. So if you want to buy 10 ice creams and they give you 200, that would be weird, right? Only order 10. That means that the recipient of the data is in complete control over how much buffer space he wants to use. You say you want 10 ice creams, you better be able to carry those 10 ice creams, right? Say you want 1 billion ice creams, you better be able to get it out of the store. So if we have this, we only send data when there is demand, right? We can only send downstream when there is demand. It means that when the consumer is faster or is signaling demand faster than the producer is essentially a push producer. He can send because he is slower. Wait a second. So if the producer is faster, it means that I can only send when somebody's asking for something. So when the consumer is slower, it means you have a pull system. Now what would be even more awesome than just having either pull or push would be an automatically switching system that automatically adapts to be push or pull depending on where needs are and how things can be produced. Aggregating the demand essentially means batching the data. If you can signal, I want 10, and then say that I want 5 more, you want 15, right? You're basically creating a batch saying that you can send 15 things to me. But you could also say, I want 1, then 1 is sent. I want 1, 1 is sent. I want 1, 1 is sent, right? That's essentially acking every single send. All right, so up until this point, we've talked about point-to-point, right? One publisher, one subscriber. It's a pretty normal relationship between streams, right? You have a very directed flow. But there's a lot of different streams that can be expressed. And one of the most common ones is when you want to sort of fan out in some way. Either you want to broadcast, right? You want to broadcast the same data to multiple subscribers. Very common. Typical use case, like your chat room thing. Something comes in, you want to send it to everybody who's in the chat room. But it's also interesting to see that when you try to split the data, you have to merge the demand. If you think about it, right? If I have multiple subscribers and I want to send to both of them in a broadcast, it means that they both have to express demand, right? Can't just send to one of them and then just drop it, because then you would have a dropping policy. But it's also inverted. If you want to take multiple streams and join them in some way, you have the tick source and the transaction or the transfer source. Same here. When you're trying to merge data into one stream, you're essentially splitting the demand. Does that make sense? So, back to some code. This is the current proposal, where it's an active specification, but this is the current proposal. Just do it quickly. We have something called a publisher. And essentially what a publisher can do is that it can have subscribers. So you can put a subscriber into a publisher using the subscribe method. And if you look at the subscriber, it has a couple of different callback style methods, right? OnSubscribe takes a subscription, and onNext means that you will get a new item. This is the callback for a new item. You have onError, which means your upstream, your publisher, has terminated for an abnormal reason. The stream is dead for a failure. So there will be no other things coming. Or you get sort of a onComplete/end of stream callback, so you know when the stream ended. And what happens, the subscription becomes sort of the shared secret between the publisher and the subscriber. And you'll see how it works in the next slide.
Note that everything returns unit here. So this is completely side effecting, you might say. But the point is to transfer things over an asynchronous boundary. So there is nothing you can strictly return at this point. So everything returns unit to make it possible to have a fully asynchronous implementation of this standard without mandating any synchronous returns.
Yeah. So what happens when you try to connect a subscriber to a publisher? So you put the subscriber into the subscribe method of the publisher, and the publisher at some point creates a subscription representing that subscriber and gives the subscription to the subscriber using the onSubscribe method call. So it's a handshake, right? If for some reason the publisher does not want to service this subscriber, it can immediately call onError and say that, I'm sorry, store's closed, something. But what happens when the data is supposed to flow? Like we've done the handshake. We should be ready for doing stuff now, right? And it all starts with the subscriber calling request on the subscription and giving it a number of elements that it wants to receive. I'm prepared to receive 10 ice creams. And now the publisher is free to send ice creams down the wire. But it can at most send as many as outstanding in terms of demand. And the subscriber might ask for more ice creams down the line, and it can even ask multiple times for more items. Perhaps something changed, right? I had a buffer size of 20, but then there was a resize thing happening, and suddenly I had twice the space, and for some reason, I can use that space and ask for more items. And then we can send even more items. So what happens when the stream completes? Well, normally you have this exchange of elements flowing down. You have demand being propagated up the flow. And at some point, the publisher just calls onComplete, saying that, okay, this is it, we're done. Do what you want to do, but I'm not going to do anything more. What happens if the stream fails, right? You have some exchange, there's some important information going across, and then at some point, when trying to produce that value, there's an exception, some socket dies, then it just sends the onError signal down and say, I'm really sorry, I can't produce any more items, and here's why. Make sense? Revolutionary?
Sounds a bit like TCP, right? So it's like all these other things. The ideas are not really that new. It's just like finding out that you need them here and implementing them in a fashion that makes sense. So this was the generic Reactive Streams project, which is about interoperability between different implementations and so on. But now we're returning to Akka Streams for some more details on that and some live coding. So Akka Streams are obviously powered by Akka actors. I just took it as a given in the beginning. Well, the reasons are quite obvious. We have this need to express asynchronous execution of signals, and actors are just made for that. That is exactly what they do. In fact, that was what motivated us to get into this whole project. Actors are location transparent. You can send to remote actors in the same way that you send to local actors. And the idea that is not currently implemented yet is that you can send streams across nodes as well in this fashion. So you can have stream processing distributed across a whole cluster of machines in a location transparent fashion. And then, of course, actors have supervision. They have this resilience built in, that there is a supervisor taking care of each of them. And, of course, we can also use that to make the stream processing pipeline, the parts of that, resilient in terms of deciding when to restart and so on, and how to recover from failures. The motivation was twofold to start this project on our end. It was that, well, we did this survey, and one of the most important things for people was that they want more type checking. Actors currently take any as a message. You can send anything you want. But if you really don't have a very flexible scenario, you just have a stream processing pipeline, then you know exactly what these data items will be at each stage. So we wanted to create a DSL for describing a type-safe composition of different actors in a processing pipeline. Now, when you do that, people have done that since several years, and on the mailing list you see the questions coming up. Yeah, I get this out-of-memory error. What happened? What went wrong? Well, of course, you need to also build in flow control. You need to respect back pressure, because otherwise, when you keep sending to that actor, the mailbox will just grow and grow until you run out of memory. And implementing all these flow control patterns is not that difficult, but having to do it yourself all the time invites mistakes, quite obviously. So we thought, let's just wrap that up and give it to people as a shrink wrap package. Yeah, I might skip this. There is a presentation by Matthias later today about the Akka HTTP, so Spray integration into Akka, which I would have had the code here. It's actually quite awesome that it fits on these few slides, but he can tell it to you much better than I can.
Enough talking, Roland.
Yeah, enough talking.
Back to coding.
Yeah, back to coding. So, yeah, we have a few minutes left, so I can do something. We had these streams of bank transfers going on. So you might recognize, I'll scroll it up. We had this flow of transfers, which we made into a producer, and the flow of ticks. Now, what we did was we made it slow, and then we converted it into euros, and then we printed it. Let's just convert it into euros right away. So we say we need to make a flow of this producer, actually, and then we can map future this thing with that's a transfer. And we call, again, this web service. There is the currency and amount. What? And then we need to actually make a transfer out of it, which is the converted one. So that's T from, T2. Then we have the currency being euros. There's a sign missing here. And this is the amount, the new one which we got. So now we have just these transfers, because you believe me that, I mean, it still works, right? I don't need to do this tuple thing. Now we have this, and it's running at full speed. There is no throttling so far. But we just want to have like one summary line per second on the screen. There is a handy thing which you can do. It's called conflate in our implementation. And for that one, I have prepared here these classes. Summary just counts the number of transfers and accumulates the amount which was in there with the plus sign here defined for it. And you can create a summary from one transfer, which starts out at the obvious values. So the first thing you need to do for conflate is to give it a constructor of your of the thing you want to aggregate into. What will happen is you get like 1 million values coming in and no demand coming up from the next processing stage, and it will keep conflating using this aggregate function, which I'll just write next, until actually someone expresses demand. And then the aggregated summary is sent downstream, and we need to create a new one to start over. So that's this part. The aggregate function, well, I made it such that it looks nice. Just add it in. And then, well, this summary thing just needs to be no, that needs to be, we don't want to do that. We need to somehow control when to pull items from this. So we use the ticks and zip it. We need to give this a name as well. Well, summarized. So we zip this with summarized. And yeah, well, we can just print that. So if we run this, well, you see, this takes a bit of time starting up and until all the actors are created and so on, which take part in this. And then it processes like 140, 160,000 transfers per second. I should have something running here somewhere. So this is HTOP. This is a quad-core machine with hyperthreading, so you see the 8 cores up there. They're all just busy, right? We produce these things as fast as we can, and then we transform them with this web service, which does the futures thing and so on. So this takes up all the cores in order to produce this 1 value per second.
Why isn't it out of memory?
Why isn't it going out of memory? Well, it is because if we look at this, if you say float this thing to a producer, it creates one actor, and this actor will be a publisher, a Reactive Streams publisher. And if you then say map future, this will turn into another actor, which is a subscriber on the one side and a publisher on the other side. The conflate thing, the same thing. It's a subscriber on the one side, publisher on the other side. And in the end, this ticks get zipped into this, and the zip will then just have one demand token like per second. But demand, so the back pressure is propagated as we have seen before, from subscriber to publisher, from subscriber to publisher, to slow everything down to keep the buffers bounded. So we do it as fast as we can here, but not faster. Right? That's the trick. That's the back pressure at work, and this is why this doesn't crash. This was the conflate. We can do a crazy thing as well.
Shouldn't we stop it?
Or are you hungry?
No, not stop the session, but shouldn't we stop the conflation?
No, it stopped.
It stopped? Felt like it was still running.
No, it's not actually.
Okay.
No.
Oh, wow.
So who's hungry?
Yes.
Who wants more streams?
More streams.
Hey, cool. So, yeah, we will not skip step 5 then. So, let's do it the other way around. So we had this web service thing, but we always hit it, like for every, 150,000 times per second. That exchange rate querying site might just not love it that much for us, love us that much for us. So we can just query it every 5 seconds and cache the result and use that to convert things as fast as we can locally, because the exchange rates don't really change 150,000 times per second. So what we do for that is we make a rate flow. This flow will be a timed one. I'll just say like 5 seconds. And then we need to say what happens every 5 seconds. In the end, we will have to return a function. But this function will have to have state here because I want to show you that it's actually doing something. I have a var current, which starts out at 1. And then the function which gets returned is just, well, what I had here, I need to scroll this up a bit. I have a function which just well, cheats a bit, goes to the web service and asks it for the current values and maps the values with the factor. So we can have some varying thing here. So what we do is current times equals 1.5. There's some real inflation going on here, right? And then we return rates multiplied by the current. So this is a flow which will give us a new mapping from currencies to exchange rates every 5 seconds. Then, well, what do we need to do here? So we take the rate flow and we need to expand it. Expand means whenever a value comes in, it gets put into this thing. It's like conflate, just inverse. And then whenever demand comes in, well, we pull out of this thing using a function extrapolate, which we have here. And we keep doing that on the same origin until we get a next seed. So the seed is just identity. We want to keep this map. And the extrapolate, well, this will just be this mapping of rates. I'll call it R. Due to some mishap with where the parentheses go, I need to actually give it the type here. That's a map from, we'll fix that. Currency to double. And what we do here, well, we just give that back, but we also need to update, we need to give it the next step, so for the next round, which will be the same. So this will just repeat the values that came in. Sorry? Code up. Yep. Thanks for the hint. It's easy to overlook here. So scream if you don't see. So this is not yet a producer of summaries. This is where the red squigglies come from. I can also just take this away if it annoys you. So now we need to actually zip this one with the inputs. Now we have pairs of the dictionary with the rates and a transfer. So we just map it right here. This would better be a case. So this is rates and the transfer T. And this gives us a new transfer. Transfer T from T2. And then we can just do the transformation right here. Let me do that like this. We have T dot. No, we have first we have currency euros. And here we need to say T amount divided by rates T currency. And because I said it's not nice to use doubles, we need to actually make it a long again. Any type checks? And so this is the mapped thing. And now we need to, did I? Yeah. To producer, that's a capital here. Okay. So, well, this doesn't quite match up because my plan was, is Andrew in the audience? Look away, yeah, please. Otherwise, he'll probably beat me afterwards for this. So we have here expanded an infinitely fast stream into something which is arbitrarily fast. Now, the really dangerous thing to do, don't do this at home, is to conflate this. Because between the two, well, things will flow arbitrarily fast, obviously, as fast as the thing can go. This is the same old trick. We do the same summary. Like this. And so we get, like with this, we zip it with the ticks again to get one summary per second. And then we just print it. I'll put this in the screen. And we consume it. Now, what happens if we run it?
Stand back.
So it's taking its time because the first currency conversion rates came in only after 5 seconds. The flow says every 5 seconds give me something. The way it's currently implemented, it waits 5 seconds. That was the initial. And now we are actually, well, we are expanding, running as fast as we can, and then conflating into these summaries, and we get 400 and something thousand transfers per second, which are converted here. One thing I should note, these are not performance numbers, for the very simple reason that we have focused on the semantics, on how it should work, on the things you can express, that we have all the combinators that are needed to implement Akka HTTP on top of it, and so on. We have not at all focused on performance so far. So don't take this as a performance measurement. And it's also not blowing up, even though we expand and conflate, due to everything being bounded inside. So that's very nice. And then...
Are you guys ready for the final? The finale?
The finale where I kill my laptop? I don't have any... Well, there's one slide, but if I can't show it, right? So we're risking everything, right? So you have seen this before. This was the one, so we zip the ticks with the input and convert it using this web service thingy. You've seen that. That's one value per second.
So one processing pipeline.
Yeah, one processing pipeline doing one thing per second. Now we create 50,000 of these, right? They will all be created next to each other. And then we merge the resulting streams. This is not yet in Akka proper, so I coded...
50,000 way merge.
Yeah, I coded up an n-way merge. It's simple. I mean, just code it up n-way, and then 50,000 is just a specialization of that one. It doesn't really matter. So this will construct a tree of binary merge stages, which merges these 50,000 streams into one stream. And then we just run this analyze function, which I've given here, here below. I should probably try to scroll this up again. So this will just average the size of the transfers and give us a string. So this means we, for each println,
you can find me over here,
consume mat, and it doesn't type check. It doesn't even type check.
Wow.
What's wrong?
The suspense.
Sequence. Oh, yeah. Well, I didn't read my own comment. I didn't do the 1 second thing yet. So this analyze expects to see one thing per second. And I have these 50,000 streams going into one, and I want to have like one thing per second. For that, we have a combinator as well. It's called group within. You can give the maximum number of elements. I mean, I don't want to limit this, really. I just want to see 1 second. Now it adds up. Grouped within gives us a stream of sequences, whatever came in within this second. Then we analyze it, and then we print it. So let's see. Just to so you can like begin to appreciate each of these streams. I told you we have done the obviously correct and really stupid implementation that everything you do with a stream becomes its own actor. So we are creating one for the input, one for the ticks, one for the zip, one for the map, blah, 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 and so on. I counted them. It's 26 actors through which every single thing goes in this pipeline.
Per stream.
Per stream.
What's 26 times 50,000?
It's a while. Also, it needs some time to create all these actors, but it actually starts and it actually prints things. This is amazing.
I don't believe it. I don't believe it, Roland.
So this, we expect 50,000 per second, and we get them. Now looking at the CPUs, well, it doesn't look too bad, right? It's a bit more than half of my total computing capacity of this computer is used.
So 1 million actors.
Yeah, so 1.3 million actors, and everything's just working, and all the little elements do what they're supposed to do. Back pressure is working across all of it, right? So that, I mean, that's just a statement you you probably don't believe me, but if I make this 100,000, obviously, I mean, the CPU was above 50%, so this is not going to work, right? This can't work. Really can't. So cores are all maxed out, right? A lot going on. This is not printing anything yet. I think it's still just trying to start these 2.5 million actors. And starting the ticks to run. This will take a while, I guess, before something comes back.
But there's no out-of-memory error.
But notice how there is no out-of-memory error. It should eventually start printing something.
I hope you're not hungry.
The VM has, I think, 1.5 gigabytes. That shouldn't be critical. Yeah, well, maybe starting all these actors takes longer than I guessed, and you don't see the printout. But still, so the thing is, this will not run out of memory, or it will not do any crazy stuff. It will just not be able to satisfy like one thing per second on each stream, because back pressure will actually push it down. So this is all I got.
Thank you.
So do you have questions? Oh, some people have questions.
Oh, wow.
How do we do it with the microphone? Or can you shout? So the question was, why didn't we just use Scala Z stream, or basically? Well, so the things which we want to express, the location transparency, the distributed aspects, especially the resilience parts and the supervision, we felt that needs our actors. So this is why we based it on our actors. We have looked at the Scala Z stream, of course, as an inspiration of what is possible and what can be done. That's for sure. Yeah. So these streams, you've heard from Victor, demand flowing one way. It's a simple method call, and data items going to on next. If something does not work there, then afterwards it's really messed up, right? So there you need to have this happening. I'm German, so I will never call it guaranteed delivery, because there is no such thing. But streams assume that method calls work. Yes, that's true.
And if they don't, it has to be terminated with a non-error.
Oh!
Finally!
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 So there was a problem. Yeah, it's version 0.3, so yeah. So if a producer has 2 consumers, how does the back pressure work? That is one thing. You can completely choose how to do it here, because everything is explicitly available. You can have this, for example, you could have the intention that all elements get propagated everywhere, and full back pressure shall ensure that all processing occurs, which means that you just propagate back pressure upstream if not both consumers are fast enough. You could also have load balancing, so you just send it to either consumer depending on which one has signaled more demand. Or you can have multiple consumers, and you say, if there is one lagging consistently, just kick it out and keep the others running faster. Or the possibilities are endless. You can model whatever semantics you want on top of that. I think that is the power of this model. Yeah? Okay, so the question was, this is all looking nice, but how do I test this, basically? So one thing which comes to mind is the flow materializer. You can write one, which we have not done yet, which does everything synchronously. So you write your for each, and you consume it, and then everything has happened, and you can assert like that the right things ended up in the right places. Other things we can do, there's a lot of research which has been done over the past 40, 50 years on Petri nets and data processing networks. So we can also provide tools which work on this description. So flow, DSL, blah, blah, gives you a syntax tree basically describing your processing. And you can make a static analysis of that one to figure out, you have a problem here. You expand and you conflate. That analysis would probably have told you that my code was not really, was maybe a bit fishy. You can do advanced analysis there. Otherwise, well, it's the same thing that you have for testing actors. It's asynchronous. So you put something into the stream, you expect the right things to happen eventually, so you assert after a timeout. That's what you typically do. Yeah? Yes, so the question was, it's built on actors, but I didn't show any actors in the live coding, basically. So are there bridges between actors and streams, right? Yes, there are. They're called actor producer and actor consumer traits, which you can mix in, which I didn't show. Do we have denotational semantics for it? No, not yet. Sorry.
Open a pull request.
So, if there are no more, oh, there's one more. That's the last one. Then you can go and have lunch. Does the flow have to be acyclic, or can it like flow back? It can flow back, yes. So you can make flows which turn things around in cycles. We have something similar to that in the HTTP implementation, actually. There is no restriction on these flows, but of course, if you send items on this circle and they keep running around or multiplier, obviously that's not going to end well. Because it's bounded, it will just deadlock at some point. So, yeah, have a nice lunch then, everybody.
Thanks, everybody.